Hello everyone. The topic of today's discussion is how do we bias the circuits that we see as amplifiers. Basically, all the CS, CG, CD, or op-amp based high gain circuits. How do we bias them? What is the general idea or issues or techniques that go in the context of biasing high gain circuits? So for high gain circuits, what we need is a very high output impedance so that the gain, that is the GM of the circuit times the R out, is high. So for high output impedance and with the use of complementary MOSFETs, the only topology is we have something like this with the two drains connected to one another, so that the impedance looking into this node is of the order of R0. Now what comes here is this condition is a very well known case of two current sources connected in series. Thus the potential here is not defined and we need to do something to set the bias at this node. So one of the commonly used techniques involve placing a resistor from the input to the output like this. And how does this help is due to the fact that since this is the gate of the MOSFET, we assume that no current flows into the gate, so there is no current to the resistor, because the input also we assume it is capacitively coupled, so there is no current that goes into the bias network DC wise, so the DC current to the resistor is 0. Hence the DC potential here, which I denote by Vi naught or V naught, will be equal to the DC potential here. So the DC potential at these two nodes will be equal, and this will solve the problem of this node potential not being defined. So now it will be equal to the input DC node potential. So this will be the case of two diode connected transistors in series, because these two are short and these two are also short. So these two can settle at certain value. When you equate the two current equations, you will get the value of the current that is flowing as well as the voltage that is developed at this node. You can solve for the voltage and then plug it back to solve for the current. So this is settled at some value of the current that is flowing and some value of the output bias voltage, which will be equal to the input, because these two will act as diode connected loads and they will no longer be high impedance. But we would need them to be high impedance since we need a higher gain. So how do we solve that problem? Because now since they are diode connected, they'll offer low impedance of the order of 1 by GM and will not be able to have high gain amplifiers. Okay, otherwise we would just have used two diode connected transistors like this, and we have directly shorted by a piece of wire. Why are we using this resistor over here is the answer to the question that why does the circuit still have a gain of the order of R0. So in order to analyze the impact of shorting the gate and drain, we would need to see the impact of R on the AC performance of the circuit. So for that, let's say we have some input which is capacitively coupled at the input node. Then we have this R, and then we have the output node. So let us assume that the gain is high, which means that the output swings are high. Now with respect to this output swings, we can neglect the output swings at the input. So we can assume that the input is virtually at ground. This is a very coarse approximation. So we would reduce the network to something like this. We'll have ROP in parallel with RON in parallel with R, since we approximated this node to be ground. We approximated this to be AC ground. Now we can see that for this to not degrade from the order of R0, we would want that R should be greater than the parallel combination of these two. So this will ensure that these are diode connected loads at DC, as well as these have the output impedance of order of R0 at AC. So this is the purpose that the resistor serves. Now a similar case can be seen in the case of when you wish to calculate in the case of an op amp. So biasing is not an issue when the op-amp is in feedback. Let's say you have a non-inverting amplifier, and the DC value here is, let's say you have the non-inverting amplifier in unity feedback, and the DC value here is Vi naught. So by the virtue of virtual short, the DC value here will also be Vi naught, and thus the output will be defined, because the second stage, if it is a two-stage op-amp, the second stage is similar to this. So we would need something to define the output voltage of the second stage, but here that is taken care by the inherent feedback present. But when I wish to measure the open circuit loop gain of the op-amp, we would need to define the output potential, because an open loop will have no condition on the output potential and it will remain undefined. So we can use the similar technique. We can place the same resistor as we placed here from output to the input. Again, the same fact, there will be no current flow because here it is the gate of the MOSFET, so there is no current through the resistor. So the DC value here and here will be equal, which will be equal to the DC value of the input that is given. Let's say this is Vi naught, then the output will also be settled at Vi naught. And here also, due to the similar argument, since this is a high gain amplifier, the swings here will be low, the swings here will be high, and you can assume this node to be ground and build a similar structure like this and have the same condition. So these two circuits are kind of analogous to each other in the terms of self-biasing. So now I think we can move on to viewing these circuits and understanding the bias networks utilized in these circuits. So we'll go one by one. First of all, M1 and M2 are the core transistors for the inverter as an amplifier. We would need to get the value at the gate of M1. We would need to get some value at the gate of M1. For that, we can put an ideal voltage source. But then there will be PVT variation, so we would go with the current mirror concept, and we would put a current mirror directly. So what are the issues of putting a current mirror directly? Are that you will have some voltage division from V in to this node, that will be given by the factor will be given by the resistance seen here, which will be 1 by Gm upon the source resistance plus 1 by Gm. This time Vi will be the signal that is seen at the gate, and if Rs is high as compared to 1 by Gm, which will be usually the case, we would have a very severe attenuation when the signal reaches from here to here. So we would need to increase the input resistance of the amplifier, since this is a voltage input amplifier. So for that, we put a large resistor, a bias resistor Rg, such that this becomes Rg plus 1 by Gm, which is close to Rg, and this is close to Vi if Rg is chosen to be greater than Rs. Next, this Cv is just to capacitively couple the input to the gate, because the bias is not coming from the input, it is coming from the current mirror network here. Next up, we have the circuitry for M2. So let's say for a moment Ig is not there. What happens at DC is Rg is a short because Cg is open and no current flows into the gate of the MOSFET. So Rg is a short and M2 is a diode connected load at DC. Now since this is a diode connected load at DC, this potential is defined because M2 is diode connected and it is a low impedance node. So this potential will settle because it will be Ib1 flowing through diode connected M2, and since M2 is diode connected, we will have this potential developed to flow Ib1 through this node, through this branch. Now the next thing is, why do we have Cg and Ig? So Cg is just to incrementally ground the gate of M2 such that the looking in impedance here can be of the order of R0, because if we don't have Cg, then we will have some swings at this node and we want to minimize those swings so that the looking in impedance here will be RO2, which will come in parallel with RO1. Now for Ig, we have Ig because without Ig, let's say the DC value here is V0, then the DC value here will also be V0. And if V0 is low, then the output DC will be low, putting M1 at a greater risk of going out of saturation because M1 will have very less headrooms. So the negative swings at the output will push M1 out of saturation. So in order to have higher swing limits at the output, we would need to increase the DC value at the output. We would want the output DC to be high such that even with negative swings, M1 will not go out of saturation. So since without Ig we cannot do anything because the DC value at the output is limited by the gate potential of M2, which is settled by the value of IB1. So if we want to get a control over Vout's DC value, we want to increase it, we add a current source Ig. Since Ig cannot flow through the cap, since it is open at DC, it cannot flow through the gate, it will flow through the RG completely. And since it flows completely through RG, this potential here will be V0 plus IgRG because Ig flows in this direction. So now we would have enough headroom for M1 and M1 will remain in saturation even for negative swings. So that is it for this bias network. Now we would come to the bias network of an actual inverter. For this circuit, what we have is a similar bias technique here, but they have these two extra components over here. Cn is just to capacitively couple the input to the gate, but these two components play a different role. So what happens is, strictly speaking, this will be out of phase. So you can draw it like these, or you can verify whether they are in phase or out of phase. Next up we have the role of I1 and C1. So what happens is the current in this branch will be dependent on the value at which this circuit settles. So when you equate the current conditions of these two transistors, when you equate the mu NC aux by 2 VGS minus VTH whole square for both of them, you will find out the value of V0, and when you back substitute the value of V0 in the expression, you will find out the value of the current I0 that flows through this branch. Now what if we would want to have some control over the value of I0? Because here the value of I0 is controlled by the equations and basically by the sizing and mobility factors and all of them. But if we want to have an exact value, or we want to have an exact number to the amount of current that is flowing through this branch, we may put a current source here. Ignore C1 for time being. For DC, this current source will define the value of the output DC. Since these two are direct connected loads, they'll accept the current that is being pumped into them, and since they are direct connected, they'll accept the current and they'll develop the gate voltages in order to flow the required I1 amount of current. Now C1 is just to make the source of M2 incrementally grounded so that the looking impedance here can be order of R0. So I think that is it for the video. Thank you for watching.